This is a narrated answer key of the Unit 12 FRQs. This is the first one. I've spread them out with space in between each one so that I can write in between, but trust me, these are the same. So if you have it open, you can watch along while I do some of these, or you could do yours and then play the video back to see which part you're doing well on. So this first one comes from 1996. Let's calculate the H plus in a 0.14 molar solution of weak acid. So this is just a basic equilibrium problem. You write out the formula HOCl splits up into OCl minus plus H plus. Ice table, original concentration is 0.14 molar, 0, 0, minus X plus X plus X, 0.14 minus X, X and X. We're going to assume that the X here is so small compared to the 0.14 that it's negligible. So when I set up the Ka expression, I get X times X, or X squared, over 0.14 is equal to the Ka, which was listed up above in the problem, 3.2 times 10 to the 8th. Negative 8th. Solve for X, and X is equal to 6.7 times 10 to the negative 5th molar, which is it. We've answered our question. It happens to be the concentration of the OCl minus and the concentration of the H plus. So there you go. H plus concentration equals that. Next up, part B. It says write the correct balance equation for a reaction between NaOCl is dissolved in water and calculate the numerical value of the equilibrium constant for the reaction. Now right off the bat, I recognize that this shares a common ion with my weak acid, so this is its conjugate base. Well, I plop the conjugate base into water, and I'm going to have OCl minus. The sodium is a cation and is a spectator. So the OCl minus is going to remove a proton from water to become HOCl and OH minus. We're looking at a base here, and we talked about in class the relationship between Ka of an acid and the Kb of its conjugate base is always multiplied together to equal Kw, which is 1.0 times 10 to the negative 14th. So if Ka is, Ka is 3.2 times 10 to the negative 8th, well, we'll put it in right here, 3.2 times 10 to the negative 8th, that's equal to the Kb, and Kb is equal to Kw, or Ka times Kb is Kw. Kw is 1 times 10 to the negative 4th, 10 to the negative 14th, and just simply solve for Kb by dividing by 3.2 times 10 to the negative 8th on each side. In this case, Kb is equal to 3.1 times 10 to the negative 7th. So we're going to use that information to do part C. Let me zoom out so you can see the whole thing. Calculate the pH of a solution by combining 40 milliliters of 0.4 molar and 10 milliliters of 0.56 molar NaOH. Now, if this was a combination of a weak acid and its conjugate base, then this would be a buffered situation. But this is a titration situation since the acid, HOCl, is being titrated with a strong base. First off, I want to determine how many moles of acid and how many moles of the titrant base are being used in after they've been mixed together. So first thing I'm going to do is take the 40 milliliters, that's the highlighter, so 40 milliliters, 0.040 liters, times the number times its molarity, 0.14. That equals 0.0056 moles of acid. Now next up I'm going to take the 10 milliliters of 0.56 molar, so 0.010 liters of 0.56 molar, which equals 0.0056 moles of base added. Since we have equal moles of acid and base, we are at equivalence. And since they've neutralized, we talked about in class, at the equivalence point, the moles of acid that get neutralized are equal to the moles of the base, the conjugate base, that get produced. So if I neutralized 0.0056 moles of acid, then at at equivalence, I have 0.0056 moles of the conjugate base, which is the OCl- ion. But I want to get the new molarity of that, and I have 40 milliliters plus 10 milliliters is 50 milliliters. So if I take the moles and divide by the liters, I get the new concentration of 0.112 molar. With that information now, I can answer the question, what's the pH in this solution? Now, since it's a weak acid with a strong base, I expect the pH to be above 7 when I'm all finished. So that's my ballpark. Just know that that's what I'm aiming for at the end here. So I set up an ice table, but I want to set up an ice table for the Kb expression. Now, up above, we wrote out the net ionic reaction and the Kb constant. So I'm gonna snag that, move that down here, and I can actually take that and resize it so it fits. Whoop. So I'm going to bring that up here. I'm going to make an ice table out of this. So I'm going to ICE, initial concentration is the 0.0, oh wait, we just calculated it, 0.112 molar. This is a liquid, so we don't care, and that's not actually part of the equilibrium expression. 0, 0, minus x, plus x, plus x, 0.112 minus x, this is x, and this is x. We'll set up the B expression just like we set up a Ka expression. It's x times x, or x squared, over 0.112 molar base, and that's equal to the Kb, which I'll snag right here. That's equal to 3.1 times 10 to the negative 7th. So I'll solve for x. X is equal to 1.8 times 10 to the negative 4th, but that's the OH concentration, not the H concentration. So to find the pH, to find the POH, I take the negative log of that number, 1.8 times 10 to the negative 4th, which gives me the POH. That's equal to 3.7, and then 14 minus 3.7 is 10.3. Now, it's important to note that this actually should be two significant figures, but I left my calculator at school. So I'm just reading the values off an answer key that I've made previously, and it's just not the right number of significant figures. So this should go 2 past the decimal, and so should this number. But this is the pH. So there's your answer to that part of the question. So let's zoom back in at letter D. How many millimoles of solid NaOH must be added to 50 milliliters of 0.2 molar HOCl to obtain a buffer solution that is pH of 7.49? After looking at this, I'm going to need a buffer solution, so I can use Henderson-Hasselbalch. I've got some acid. In my game plan, I'm going to set up a Henderson-Hasselbalch and write out what I know and what I'm trying to find. So first up, I'm going to write out Henderson-Hasselbalch. So I need the pH to be 7.49, and that's equal to the pKa plus log of base concentration over acid concentration. So the Ka from up above was 3.2 times 10 to the negative 8th. So if I want to find the pKa, take the negative log of 3.2 times 10 to the negative 8th. The pKa happens to be 7.49. Now that's particularly interesting because, as I talked about in class, when your pH is equal to your pKa, you are at half titration. pH equals pKa. The result is 1/2 to the end point, or 1/2 up to the titration neutralization point. So in other words, what that means is that if you take the original concentration of your HOCl and cut it in half, you are halfway to the neutralization point. Now, so let's calculate the number of moles of HOCl that I have. So I'm going to kind of put a pin in this side of the problem and do the next part. So remember, I'm trying to take the moles of HOCl and cut it in half, because that's half to the titration point. And I'm cutting it in half by adding NaOH to the solution. So take 50 milliliters, or 0.050 liters, multiplied by 0.20 molar to figure out the number of moles of stuff that I am creating. And the number of moles of stuff of HOCl is 0.010 moles initially. So how many moles of NaOH do I need to add to get this to cut in half? Or essentially, minus X, what do I need to add to this, or basically what do I need to subtract from this to get it down to half the original number of moles? Well, this is pretty easy. If you take 0.010 minus X, and that's equal to 0.005, then X, solve for X. Solve for X, subtract 0.010 on each side. So you get negative X is equal to negative 0.005. And then negative on 1 on both sides. X is equal to 0.005 moles. Or, in other words, that's the number of moles of NaOH that is added to the acid to cut it in half. So that answers the question. How many moles? Would actually ask how many millimoles. So move the decimal 3 to the right, and it's 5.0 millimoles, and that's your answer. Finally, the last question asks about household bleach. So calculate the pH of the solution that you see up above. And I know the concentration of this is 0.065 molar. So this right here is 0.065 molar. And I know that it's in equilibrium. Okay, this is a solution at equilibrium. So if that's the concentration of the solution at equilibrium, and the mole ratio is 1:1, so for every mole of HOCl, I should get equivalent number of moles or molarity of H+. 1:1 ratio. And this is the concentration at equilibrium, so this must be the concentration at equilibrium. And so if I take the negative log of 0.065 molar, I get the pH of 1.2. And that's the pH of this solution. Here's the second one from the sheet. Part A, the amount of salicylic acid in a single aspirin tablet is 325 milligrams, yet the tablet has a mass of 2 grams. Calculate the percent by mass of salicylic acid in the tablet. Well, it's pretty simple. You just take this divided by this, but you have to make sure that 325 milligrams is in grams. So convert 325 milligrams to grams. What you have is 0.325 grams of acetylsalicylic acid. I'm going to refer to it as ASA from now on. That's the acetylsalicylic acid. The mass of the tablet is 2 grams. So what's the percent by mass? 16.3%. This next part kind of takes us back to our stoichiometry time back in first trimester. So acetylsalicylic acid is made up of carbon, the hydrogen, and oxygen. We'll call it CXHYOZ. We know it combusts with oxygen, and we know it creates CO2 and H2O. It goes on to talk about how the combustion of 3 grams of the substance yields 1.2 grams of water and 3.72 liters of dry carbon dioxide, measured at 750 millimeters of mercury at 25 degrees Celsius, which is standard temperature and pressure. Calculate the mass of each element in the 3-gram sample. So what we're looking at here is first identifying what percent of carbon is in CO2, and then what percentage of hydrogen is in H2O. So carbon is 12.01 grams for every 44.0 1 grams of CO2. So that's the percent by mass of carbon in CO2. The answer there is 27% or 0.273 carbon in CO2. The next one is hydrogen in water. So hydrogen is 1.01, so there's two of them, so it's 2.02 grams of H in 18.02 grams of H2O. So if you break that down in percent or leave it in decimal, grams of H in H2O. Now, in the problem it says that it yields 12 grams, 1.2 grams of water. So of that 1.2 grams of water, 0.112 grams is hydrogen. So multiply those two together and you'll figure out how many grams of hydrogen are in water. And law of conservation of mass says since hydrogen's the only source of water's the only source of hydrogen on the product side, then you have equal mass on the product side as you do the reactant side. So if I take 0.112 grams times 1.2 grams, or I guess 0.112%, because that's not the grams hydrogen, it's the percent hydrogen. This is the percent by carbon and CO2. Anyway, you get the idea. The answer is 0.13 grams of hydrogen. Do the same thing, 0.273 times the mass from the problem of carbon dioxide, which was 3.72 liters. Now, because I have liters, I can't really multiply this by the 27% right now. I need to use liters and use Pivnert to convert to moles of CO2 and then do a quick molar mass conversion to convert to grams. So I'm given enough information to get to grams of carbon dioxide eventually. But I've got 3.72 liters and the pressure is 750 millimeters of mercury. And that's equal to, that's the pressure, that's equal to N times R, and I'm going to be right back with the R. I'm going to have to look this up because I don't know the R constant in terms of millimeters of mercury. But my T is 25 degrees Celsius or 298 Kelvin. So I'm going to quick look up R in millimeters of mercury and then solve for N. The number for R in millimeters of mercury is actually listed on your constant sheet, the green one. It's 62.36. So if I do this and I solve for N and multiply these all together and solve using algebra, N is going to equal 0.150 moles of CO2. And using quick molar mass, 1 mole of CO2 is equal to 44.01 grams of CO2. So then I can quickly calculate that I have 6.00 grams of CO2. So I go back over here and I take the mass percent and multiply by 6.00 grams of C, and I get 1.80 grams of C. Now, just like the hydrogen before, since CO2 is the only source of carbon in the product side, then the mass of the carbon that I just calculated has to equal the mass of the carbon in the acetylsalicylic acid. So I've got two numbers now. I know that the mass of the tablet has to be 3 grams total, and I know that has to equal the mass of the carbon, which is 1.8 grams, plus the mass of the hydrogen, which is 1.3 grams, plus the mass of the O2 of the oxygen. It's the only one I don't know. So basic subtraction gives me, and solving for grams of oxygen equals 1.07 grams. So now I've got the three answers I need: grams of oxygen, grams of hydrogen, grams of carbon. So let's move on to part C. Now, after reading this problem, I find that we're at the equivalence point, so that if I take the volume times the molarity of the base that I titrated, it has to equal the moles of the acetylsalicylic acid originally in the solution. Once I figure that out, then I can figure out the molar mass. So let's talk about the calculations here. 0.08843 liters times 0.102 molar NaOH gives me a number of moles that's equal to 0.00902 moles of NaOH. And that's equal to the moles of acetylsalicylic acid. So I have 0.00902 moles of acetylsalicylic acid. Molar mass is defined as grams of substance per mole, and the grams of substance says the student dissolves pure acetylsalicylic acid of 1.625 grams, and I knew by stoichiometry that number of grams is equal to this many moles of NaOH, so I can divide by 0.00902 moles, grams per mole, and I get a molar mass of 180 grams per mole of acetylsalicylic acid. Finally, part D. Zoom out so we can see the full problem. Now I really like this first question, part D1, because it makes you really use stuff that we've worked with, but in a new way. So pay close attention. So the first thing we want to know is, like, what's the concentration of the acetylsalicylic acid initially? This is the number of moles dissolved in 15 milliliters of water. So we can quick calculate the molarity initially. So take 2.00 times 10 to the negative third moles divided by liters of 0.0150 liters, and the initial concentration is 0.133 molar. Now let's begin setting up my ice table. Acetylsalicylic acid decomposes into H plus, and then salicylic acid minus. It loses a hydrogen. We're just going to call it acetylsalicylic acid minus. Deprotonated version. So ice table, ICE, and this is the original concentration, 1.33 molar. I initially have 0 of this. Now, I'm not going to, normally we put X's in for the change, but actually it turns out that because of the data table, I know the equilibrium concentration of the H+. If I scroll over, before any of the titrant was added, the pH was 2.22, which means before the reaction, the titration happened, I know that 10 to the negative 2.22 power equals the concentration of the H+ at equilibrium, and that number is 6.03 times 10 to the negative third molar. Well, that number is going to go right over here. That is the equilibrium concentration of, and if I could shrink that down, that'd be nice. Awesome, that's the equilibrium concentration of the H+, which happens to be the equilibrium concentration of the conjugate base, and those happen to also be the changes. If you know the initial and you know the final, you know the change. The change was plus that, and the change was also for the other one plus that, so I'll just slap that in there. And in this case, the change was minus 6.03 times 10 to the negative third. So if I take right here 0.133 minus 6.03 times 10 to the negative third, I get 0.127 molar. That's E. So I'm going to erase that, and I'm going to put 0.127 molar. Clean this up just so that I've got my equilibrium concentrations of the three substances, and so I calculate Ka. It's 6.03 times 10 to the negative third times 2, or squared, over 0.127. And Ka will equal 2.86 times 10 to the negative fourth. That's the Ka. So just to review, I used the initial moles and volume to figure out the initial concentration, which is here, and I put that into my ice table with zeros for the initial concentration of H plus and acetylsalicylic acid conjugate base. Then I used the volume and pH table to figure out the pH at equilibrium before any titrant was added. By taking the 10 to the negative 2.22, you get the concentration of 6.03 times 10 to the negative third, so that plops here, and it's also the concentration of acetylsalicylic acid conjugate base. And if I know the initial and final, I know the change, so I applied the change to acetylsalicylic acid initially and found the concentration to be 0.127, and then I just plugged it into the Ka. So finally, we're going to tackle D2. Now, the first thing I like to do when I tackle these titration problems is write out the balanced chemical reaction. So I got my acid and my base titrant, and it's going to make water and a salt. The salt, and specifically the conjugate base, which is the ASA minus. That's the conjugate base. So you've got acid, base, conjugate base. Now in a titration, you titrate moles to moles. So from the original problem, I know that I have 2 times 10 to the negative third moles of this times 10 to the negative third. Now based on the concentration of the NaOH and how much is added, I can figure out how many moles of NaOH got added to the moles of acetylsalicylic acid. So 25 milliliters, or 0.0250 liters, times the molarity, and just to remind myself, I think it's 0.1, but let's go back to the original problem. Yep, it's right up here. It's 0.1 molar NaOH. Zoom back in down here and multiply by 0.100 moles per liter to get 0.00250 moles of that stuff added, which is basically more than this acetylsalicylic acid. If I expand this out, I have 0.00200 moles. So I'm going to be adding, if I subtract, because this is going to, acid adds to the, the base adds to the acid, it's going to reduce the acid to 0. And so you're going to be able, so you're going to subtract 0.00200 moles of this to get 0, and you're going to have the same subtracted here. So you're going to have 0.00050 moles of this junk left over. New volume, though, you had 25 milliliters of the base, and it was added to 15 milliliters, so the new volume is 40 milliliters, or 0.040 liters. So I'll put a box around this. This is what I'm going to do to calculate the concentration. This number, 0.00050 moles divided by 0.040 liters, gives you a molarity of 0.0125 molar. And since this is the concentration of a strong base, the pH of the solution is dependent only on the presence of the strong base. So just take the negative log of that base, which gives you the 0.0125 molar, gives you the pOH. The pOH is equal to 1.903, so the pH must be 14 minus 1.903, which then gives you a number of 12.097. And that's the pH. This one hopefully will be the shortest of the three. This is the last one from 1977. The first part, calculate the hydronium. And remember, hydronium is the same as saying calculate the H plus solution. Basic ice table stuff. If you want to skip the ice table, you know that it's going to be X times X over the original concentration of 0.050 molar. And that's going to set equal to 3.1 times 10 to the negative 8th. Now it looks like they really like this hypochlorous acid, and this is the same acid from the first problem. Ka value is slightly different. You just work with the Ka values that are given to you in the problem. You don't try and account for them separately. So if you just basically solve for x here, assuming, once again, this is actually minus x, but we're going to assume this is so small that it's negligible. So we can just pretty much cross it out I'm going to scribble it out with blue. So all you've got is multiply by 0.05 on each side, so you've got x squared is equal to 1.55 times 10 to the negative 9th, and then the square root of each x is equal to 3.9 times 10 to the negative 5th molar, which is equal to the H plus, or hydronium concentration. So that's the answer to A. Let's scroll down to B. You're basically setting up a common ion or a buffer situation. It says you calculate the concentration of hydronium ion in a solution prepared by mixing equal volumes of 0.5 molar and 0.2 molar sodium hypochlorite. Henderson Hasselbeck does a nice job of making this easy. pKa plus the log of base over acid. So my pKa is the negative log of 3.1 times 10 to the negative 8th. I do believe. Let's just double check. Yep. I'll scroll up to A and see that. And that's plus the log of my base, which is the 0.020 molar. That's this stuff right here, 0.020 molar sodium hypochlorite. That's the conjugate base of the weak acid. So that's the molarity of that, and the molarity of this is 0.05 molar. So if I just punch that into my calculator, the negative log of 3.1 times 10 to the negative 8th is 7.51. The log of 0.020 divided by 0.050 is negative 0.40. So if I just add those together, I will get 7.11. But I need to calculate the hydronium ion concentration, so I'll just quick do 10 to the negative 7.11 power to get the H plus concentration. And that equals 7.8 times 10 to the negative 8th molar. That's the hydronium or H plus concentration. So finally, let's move on to letter C. This is very similar to the last question, letter E, on the very first one that we've gone over, and basically adding chlorine to water. This one looks a little bit different, but the same concept. This is an HOCl concentration at equilibrium. Since it's at equilibrium, the HOCl is equal to the HCl concentration. And the HCl is a strong acid, which is 100% ionized. So if that's the case, the concentration of 0.0040 molar is equal to the concentration of 0.0040 molar HCl. And the HCl is strong, so what you have is 0.004 molar H plus ions as well. And then, well, that's it. Like, you take the negative log of 0.0040 to find the pH, because this particular question, this reaction has reached equilibrium, because this is what they're telling you is there's a concentration of one of the products at equilibrium. Take the negative log of that, and you should get 2.40 as the pH, and that's the answer.